Hi, Chem students. Now that we've learned about the empirical gas laws, it's time to go on a little bit further and see if we can come up with an analytic solution, or see if someone else has actually, that matches it, which is the goal of a lot of science, is to have both theory and experiment match. And what we saw before was experiment. So let's imagine that there's a theory out there, and it's called the kinetic molecular theory. And what this really is, it's less of a theory, more of a model, where we've modeled what we think a perfect gas is. And by model, we mean we've said, hey, we think a gas has these properties. And we simplify it because otherwise the math is just too darn hard. So you make the simplest assumptions you can, but try to keep the big picture of what a gas would behave like in your assumption. So here's the assumptions that are made in the kinetic molecular theory. First off, gases are perfect spheres, meaning they're just perfectly spherical. They don't have any rough edges and stuff. We know that's not true. Just think about water. It's a bent molecule. But still, at the time, this was a really good approximation of how things behaved. Also, gases are very, very small, so their volume is negligible compared to their container. That's pretty true. Gas particles only differ by their mass, so we're not letting them have other properties other than mass. If they all have negligible volume, that's not important. They're all the same shape, so that's not important. So the only thing that's different is the actual mass of the particles. So something like water, a gaseous water molecule was 18.02 grams per mole. Carbon dioxide, on the other hand, is around 44. So they differ by only their mass. So if you're thinking of a molecule that's moving, just like anything else with Newton's laws, they keep moving in a straight line until they bump into something else, or a force is acted upon them. And we're assuming that they're so small and they're so light that not even gravity really makes a difference here. So they move in a straight line unless they hit something else. Some people call this, they move in rapid random straight line motion. The only time that they'll transfer energy around is when they collide. So they don't emit any energy or absorb any energy, according to this theory. The only way to get energy to and from them is when they bump into something else. And then finally, or I guess this is close to the end, gases don't feel any attractive or repulsive forces. So unlike things that are sticky or stick together or clump together, like into a solid or a liquid, these ideal, or this model gas, does not have any attractive or repulsive forces to make it swerve or curve towards something else. So what happens is, using Newtonian physics, you can apply the physics to this type of particle. And if you do so, it's oddly familiar. You get the exact same equation, PV equals nRT. They actually have it slightly different. They use a capital N and they use a K, meaning the Boltzmann constant. But they're the same thing, just one is per mole and one is per molecule. So for us, this is a great thing. We get the same result, PV equals nRT, from a theory using Newton's laws, which up until the 1920s was considered perfect and unyielding. And so this was a great day for science in every aspect. I would suppose there was partying in the streets wherever the scientists hung out. In any case, here's the thing. What you can do is, just like for any other time with the ideal gas law, we can rearrange this for all the variables we wanted to. And we now have a nice little equation that's both experimentally and theoretically created, and we trust it pretty well. We can measure P, V, and T really accurately, and therefore this becomes a way to count the number of moles in a container. So if you think about it, this is a great way to measure something and get the number of moles. Find out the pressure that the gas is creating in a particular volume at a particular temperature. So there are some interesting results that come out from the kinetic molecular theory. It's a statistical theory because it treats these individual particles as a big collection of particles. And in doing all the math in the kinetic molecular theory, it turns out there's finally a definition for what temperature is. And up until now, we've not really known what it is, but the kinetic molecular theory gives us that. It says that the temperature is a measurement of the average kinetic energy. Now, it's not equal to it, it's proportional to it. But the key thing is, it's proportional to this average kinetic energy that these molecules have. And that tells us something very important. If it's an average, that means that not all molecules are moving at the same speed. Think about it. If you take a test and I say the average is 75, it doesn't mean that everyone got a 75. It means if we summed up all the scores and divided by the total number of people there, we would get a 75. Same thing here. When we get the temperature, it is some kind of average of some kind of motion of the molecules, this average translational kinetic energy. We get two neat little outcomes from just looking at this one equation right here. Okay, the first is, what if I had the same gas at two different temperatures? Well, if there's two different temperatures, that means that the average velocity of the gas must be different. Why? The mass is the same. It's the same type of gas, so the mass is the same. If we increase the temperature, that means the average squared velocity must increase. So when we look at this curve here, here's a curve called a Maxwell-Boltzmann distribution. And this Maxwell-Boltzmann distribution, by the way, is my favorite graph because it explains so many things in science. But here's the distribution, this solid line of a gas at one temperature. Here, the dotted line is also the curve for a gas at a different temperature. So this is the same gas at two different temperatures. Which curve do you think is the higher temperature? Well, once again, if we go back up here and we think about the higher temperature is going to have the higher average velocity. And this x-axis down here, that's the velocity. Which of these do you think has molecules moving at a higher average velocity? I'm hoping that your instincts are saying it's this dotted line, because if you take a good close look at it, it's got more molecules moving at higher velocities, because that's what this curve is saying. If I go to 400 and I go up, this says that there's a probability of finding a molecule. It's fairly low, but there's a probability of finding a molecule going at 400 at about 0.005. If I do the same thing for the other graph, it moves closer to 0.008. Not quite 0.008, but a little bit higher. So there's a higher probability of moving at 400 for this dashed line than for the solid line. All right, let's look at one other option, and that is what happens when we look at two gases, okay, two different gases at the same temperature. So in this case, they have the same temperature, but different masses. Why? Because they're not necessarily the same gas. So if I have a different mass, then the only way for these two things to have the same temperature is if the average velocity is different. So if I increase the mass, the average velocity better decrease. Increase the mass, decrease the average velocity. So of these two curves, here's one curve, here's another curve, which is the heavier molecule? Once again, if I increase the mass, I'm going to have a lower average velocity, and this tall peak is going to have a lower average velocity. Its average velocity is actually somewhere near this peak, just a little bit to the right of the peak. That being said, the average is roughly around 200 meters per second, while this other one has an average roughly 390, 375. So what we've just learned is we can tell a lot about a gas and identify some aspects of a gas by looking at just its Maxwell-Boltzmann distribution. And that distribution is based upon the statistics of the temperature being an average quantity. So one last thing to look at is a simulation of the random motion that we see in the gases. And if we look, some of these molecules are moving very slowly while others are moving quicker. And the only time they change, I'm following this particular red ball right here, is when they bump into something else. Then they can speed up and slow down based upon how that interaction happens. So if you follow this for a few more seconds, you'll see some more of the molecules bouncing around and slowing down. Take a look at this guy right here. Going very slow until it gets bumped into. Now it's moving faster. That's what's going on in the gas state. They're just randomly moving around, kind of like the ping pong balls in the lotto drawing. Well, I hope this helps you understand a little bit more about how gases behave.